here. It's like, welcome back. So I'm, yeah. Jim McFarland suggested we talk a little bit. I am working with Christoph Bornger on integrated assessment models with overlapping generations. And when I signed up to do this, I kind of anticipated that I'd have that model sort of up and running, ready to go. Unfortunately, it's not come as quickly along as I expected, not due to any dramatic problems, more getting pulled in multiple directions. So I thought it would be fun. So today I'm just going to go through this basic, get rid of this thing. So I thought I'd go back and just review this sequential recalibration procedure and share. I'll go through some slides from a workshop we held at ETH a number of years ago, and I'll share the program files that go with that. So this is an opportunity for people who are working with working with dynamic models to perhaps think about ways that they could actually set up their models to work with overlapping generations. And this is, I'm thinking primarily about the group at EPA. You have this this multisectoral dynamic model, and the procedure we have is something that's would be perfectly suited if you wanted to move from a representative agent, infinitely live representative agent model to a overlapping generations model. This is a method that you can use without necessarily changing your representative agent model very much. It involves solving a sequence of equilibria where you sort of solve your forward-looking model with the policy, and then you go out and take the prices from that solution to evaluate the household responses, the individual household responses, and then once you have those, you go back and recalibrate to calculate a different representative agent model. So it's actually similar in spirit to sort of a Negishi style model where you change the weights on the households, but here you have to do want to change the weights on the different goods. So it's a little bit different, but I'll go through that code and I'll also point to some code. I don't know if there are other folks in the model, so I guess I'm thinking more about my audience as being mainly the group at EPA, but if you have questions about sort of dynamics, I can point you to that. And I just say, so if the OLG stuff seems complicated, again, it's kind of embarrassing compared to how nicely organized Jim's stuff is, but the mpsg.org has this link with MPSG stuff. And if you do a search for, say, dynamic, then there's a whole section on dynamic general equilibrium modeling. Lots of different things here, but if we look at, if I target state variable, state variable targeting. So here's one. So there's several different papers here. I really like the state variable targeting technique. This is sort of assumed that you know that the OLG method assumes you know how to set up a dynamic model, which is forward looking. And so this is I'd suggest for thinking about how to do this, I'd say begin with this NLP model. Is a nice sort of example. It's a sort of a Ramsey model: consumption plus investment equals output. Output is a Cobb-Douglas function of capital and labor, so it's the generic. This actually may be solvable actually in closed form. I'm not even sure, but 10-year time intervals, and then it has terminal capital stock. And the key trick that we do for solving dynamic models to make it sort of finite is to focus on what the state variable is at, and maybe multiple state variables at the end of the horizon. And so it just basically involves projecting what those state variables are, tying them down, solving the optimization problem, and that the state variables then essentially truncate the finite horizon model with the infinite horizon approximation, and that gives you a technique for getting things to converge. I mean, in this model, if we look at so here's an investment plot of investment in this model, and you can see you get very little. The whole trick here is that this shows you very little approximation errors. If you go through 2010, 2020, 2030, 2040, see that there's very little approximation error if you handle the state with the state variable targeting. It takes a little bit of time for it to converge. So this shows this example of what's happening. You have this when you first target, if the target being 0, then essentially investment goes to 0 at the end. And then gradually you increase the target to project where it should be. And so the idea is that you fix the target, solve the model, and then from other variables in the model, project where a capital stock should be, and then you readjust it. And so this basically shows the sequence 12 iterations. So I'm beginning from the assumption that we're comfortable with how to handle sort of the representative agent or the infinite horizon model, and then we'll move into talking about what happens when we want to add lots of households in the setting. So we just get this back.
Can you
Hey, Sean, you're not sharing your screen.
Share my screen.
Yeah.
That's stupid. So again, here now I've gone through this without explaining what was going on. So I basically, what I was showing you was, if you go to the MPSG page, mpsg.org, if you've not done dynamic modeling, that's just beginning with the state variable targeting in an NLP framework. That's sort of a nice examples. There's a number of other questions about the Ramsey model, but there's yet another paper introducing dynamic general equilibrium with MPSG. So this is also a useful place to start. But there's a variety of different pages here. But these little ones are very nice because they have GAMS code that goes with them. So this guy basically goes through the whole thing. So I'm not going to go back and go through that, but I'm just pointing you to that's where to look if you wanted to sort of pick up where I'm starting from. Okay, so now I'm going to go to Sebastian Rouse's work. So that's going to be OLG decomposition notes. So hide meeting controls. This guy should be. So you can see this is from a long time ago. This is like 12 years ago. The thing that's different that I'm working on now with Christoph on the OLG is we're working on models that are non-stationary growth paths. So that way I'd like to be able to, all I'll show you today is basically stuff where we set up an OLG model where we have a steady state, and that gives you a very easy way to calibrate to a baseline. And it's the standard sort of approach, but I've been experimenting with methods for having a non-stationary baseline so you can impose assumptions about GDP growth and so forth and still have the model sort of latch onto that. So you have to solve, to do this, you have to solve a calibration problem that's forward-looking. I don't think it'll change the results that much, but it's one of these things. It's the energy modeling model. There's this presumption that people look carefully at your baseline, and so I'm trying to make this possible. I also have this thing on my list of things to do before I retire. Is I want to go back to this paper I wrote a long time ago about the intergenerational burden sharing in climate policy, and I think that that's something I find intriguing. There's a so there's it's a sort of a cool topic in general. I'd like to go back and revisit this literature. But for today, I'm just going to go through what we did for this approach. And so I'll go through the basic sort of idea here. Is a computable OLG in the tradition of Auerbach and Kotlikoff have been important tools for economic analysis for a long time. And their early paper, the early Auerbach and Kotlikoff 87, man, these guys were way ahead of their time because they were able to set up this model and they're not numerical. They didn't use any fancy numerical method, but they just came up with a clever, intuitive way of solving models. I was really impressed. Their work is great. So here, but the challenge with it is that the method they had was, while they were able to do it for the sort of macro models they were working with, if you want to work in a setting where you have, for example, multiple sectors, or if you want to work in the OLG model where you have both energy technologies, you have a transition to some sort of backstop, or you want to look at the role of technical change, anything that involves lots of sectors, then it's always a challenge to figure out how to embed the OLG sort of setting in that framework. So this is good. What I'm going to go through today is a technique that if you can solve the Ramsey model forward looking, then you're off and running. So this is basically, it requires some iterations, but basically it's a projection method which we found had good luck with, and I think it's a useful starting point because it's relatively low cost. Indeed, the work we're working with the integrated assessment model, the main challenge is the non-stationary baselines where we're spending most of our time working on. So all these models typically involve a large number of variables and equations describing the equilibrium behavior. Computational complexity may limit the application, and that's one of the challenges for, if you try to solve these guys simultaneously, then you end up with really high dimensions because you have both a temporal dimension as well as a household dimension, because you want to have household born in every period. And so that's the challenge. So our objective here was to develop a computational approach that could solve large scale models. And we found that this approach was based on some work that I did with David Tarr on a model for Russia. So I'll explain a little bit about how this works. So I'll go through the technique we're using is a technique for dealing with disaggregate households in a GE setting, and it could be applied either to a static or a dynamic model. Indeed, the first application was to a static model. So let's just think about, my first example will be going through a static model. I don't know if I have the story here. So it's a story. Have I told this? I'm getting old enough. I don't know if I've told stories. I've probably told you this story many times, but so we were working on WTO accession for Russia, and the main challenge was just that we wanted to get data for households, and Gus Comstock, the statistical agency, was willing. We knew they had a large household survey that said exactly where people made their money and where they spent it. So that's exactly what you need for getting distributional effects. And they basically were willing to share the data set with us with one condition, and that was they'll give us the data set as long as every household goes in the model. That was essentially what the guy said. Okay, 54,000 households. We'll give you the data set, provided we want to see the model effects on every single household. So it's this crazy thing. Part of it was we just didn't know our way around the block. This is another side story. So we go to Gus Comstock to get the data set. We go upstairs, this big back and forth. I think they still had stuff on computer tapes, and we have to get the thing. And then I come out of the front door of Gus Comstock on the street. It looks like a food cart, but actually I look at it again, and it's actually the guy's got CDs. He's selling CDs. Man, that's funny, a music store out in front of the statistical agency. And then I look more carefully, and the CDs are actually data. And so it's basically, I got the more recent version of the data set was available from the guy in the street. So you pay him $20 and they'll give you the data set that they're going to release in 6 months, right? So it's like, so anyway, but unfortunately we had to have approval. This was a World Bank project. So if we couldn't actually just have black market data and then publish it, that would have been not allowed, but it was kind of funny. So now we suppose we have a household. So this is CES preferences, and this is going back to stuff I talked about yesterday morning. So we have preferences, the standard homothetic preference CES technology has an elasticity of substitution, which determines rho. Rho is equal to 1 minus 1 over the elasticity. So as sigma, the elasticity substitution goes to 0, rho goes to minus infinity. When sigma is equal to 1, then rho goes to 0. So it's got a point in the parameter space where it has a special form. It's the Cobb-Douglas form is the limiting case as rho approaches 0. And then as sigma goes to infinity, then rho goes to 1. So that's the basic sort of set of parameters. And calibration involves converting observations of choices to determining what the value is. So alpha gets determined as a function of sigma or rho and a set of observations of prices and quantities. So I get to observe, if you tell me what the value is of sigma, I know rho, and if I get one additional point, if I can find what you consumed at what prices, then I know what alpha is. So that's the assignment here. And so that says we can scale. It's arbitrarily, it's independent of scale. So you could scale the alphas to sum to 1, but whatever, you can basically, and then there's one free parameter. So that's a convenient way to represent this. And again, this is what I emphasized on the week, is if you over parameterize the model and you introduce both a value share theta and a point C bar, then you can basically calibrate it. It's as though you have an indifference curve and you can pick any point on the indifference curve to calibrate the function at that point. So the calibration point is not, the same preferences can be produced from many different calibration points. So if I've given P bar and C bar, then I know how to calibrate theta. The theta is going to be the value share that's spent at that point. And so that gives me the utility function on the primal side, and we get the unit expenditure function on the dual side as a function of those parameters. We get the indirect utility function. You have sort of demand functions. It's all well defined in that setting. So that's the calibration technique if you're given data. So the basic idea we're going to do here is that normally we think about observing aggregate demand at a given price point, make an assumption about elasticities, and calibrate the preferences of the representative agent. Here we're going to do something different. We're going to say, we're going to take an estimate of what the prices are in the current equilibrium. We go out and evaluate the demand response of many households, and then we're going to use that demand response to parameterize the representative agent. So the representative agent is a synthetic construct which is used to approximate what the demand response are of households. And then that calibration will be repeated to the point where we have consistency between the representative agent model preferences and the household model. Because if indeed at the given candidate prices, if the representative agent demand is the same as a household demand, you are in equilibrium. So this will make it possible to separate out the demand response of the households is then completely separated from the demand response of the representative agent. So let's look at an example. So each household, so theta sub IH is the benchmark value share for household H. C bar sub IH is the benchmark consumption. Those parameters, theta IH and C bar IH, those don't change. So those are given. We're assuming those are data. The thing that's trickier is like econometrically, how do you evaluate then what the value is of rho? So you probably need more than one point to evaluate rho, but imagine the preferences of the household are all observed. So now, if we want to portray this, we want to portray these demands using a representative agent. Now I'm going to introduce an index K, which represents the iterations. So this means that the representative agent's decisions are going to change from iteration to iteration. The household choices don't change, but the representative agent does change. So theta K sub I and C bar K sub I are the representative agent value shares and consumption points in the current iteration, and that's going to change from iteration to iteration. So how do we, if we have a set of prices, you give me prices, that's factor prices and goods prices, I can then go out and evaluate what the household choices are at that point. But here, so initially, let's begin at K equals 0. At K equals 0, the representative agents' demands are the same as the households. The value shares are the same as the agents, where we assume that all of the agent consumption choices are observed at the same common set of commodity prices. And that will give us our representative agent. And we've basically noticed that the curvature of the representative agent indifference curve is more or less arbitrary. We're going to have better performance if we pick the elasticity rho to be approximately consistent with the rho H. So rho H is the household elasticity parameter. Rho is the representative agent elasticity, but it doesn't really matter. If we pick a very different value of rho for the representative agent, we may have to iterate more, but otherwise we find it doesn't matter that much. So here's the initial point. There's the benchmark equilibrium. Then we're going to do a policy shock. Russia joins the WTO. They liberalize business service firms that can move in. There's a big change. There's Dixit-Stiglitz variety effects coming from the introduction of many new varieties. There's big productivity gains in the economy. There's a big improvement in aggregate income. And our representative agent model predicts that consumption will move from A to B. So that's from the representative agent model, who's initially calibrated at A. But once we have the prices at B, we can say, well, wait a minute. I wonder where consumption would truly go if all the households were evaluated separately. So that in that case, we're going to say is take the prices that we got at B for the representative agent model and go out and evaluate what the demand responses are for all the households at those prices. And so that's going to be a point C, which is not the same as B. It may be that they're close. If the elasticity response is roughly the same, you may be lucky, but there's no guarantee. Particularly for the first iteration, it's likely not going to be because it's a big price change, a big productivity change. So the budget line shifts a lot. Productivity, it shifts everything over. So So, okay, so you could end at that point saying, well, we used a representative agent model, we got this solution, and we can tell it's not the right solution. Sorry, our model's not able to handle households. So that's the normal trade approach, is to assume you have costless redistribution and say, well, we don't really know what happens to households, but we know that we generate enough money, we can bribe everybody to go along with this. That's the standard sort of trade story. In fact, we may want to say, no, wait a minute, who actually loses, who gains in the story? So that might say then, okay, what's the change? And you might say, wait a minute, we have a new set of prices and we have a new aggregate consumption point. So we have a consumption point at C. We know the prices at C. We could take the representative agent and say, wait a minute, let's think about a different model. This is a completely different model, where our representative agent is not characterized by the preferences that we calibrated at A, but the preferences are described by what we've calibrated at the new point C. So we basically say, throw away that old representative agent and wait a minute, try this new guy. This guy's calibrated to the new prices. So basically, to do that point, you have to say at the iteration K-1, you evaluate what the household demands are at that point. That's the CHI of P. And you evaluate what the value shares are at that point. Boom, that gives us a new representative agent demand function. Real households are never altered, but all we do then is we just repeat that process. And typically what happens is the first iteration, if it's a big policy change, Russia joins the WTO, big productivity change, if you have a model that's got a sort of industrial organization story going on, it could be lots of stuff happens. But then the subsequent iterations are just going to be changes in the demand structure, which are small relative, because the subsequent iterations, if we resolve the model at C, it's going to be a relatively minor change, not a major change. So you move from C, you move down to D. Basically, the PPF gets shifted out by the policy, and thereafter the PPF is going to be unchanged because the policy changes occurs in the first iteration, and all the rest of it is just retuning where the demand, what happens to the representative agent. So that gives us our procedure that we can adopt, and this was a technique that we adopted so that we could get the data from Gus Comstock. And looking back on it now, it's incredible reading about the delusion of the West at the idea that Russia would change. We really believed that WTO accession. At the time I was working on this project, I was convinced that this would change. But there were points during the project when I went to present results a few years after the paper got published. I went to a project at St. Petersburg, and I met a group from the ILO, and they were looking at our results, and they're telling us that one of the sectors we had expanding was like, I don't know, raw materials or some of these things. And they said, the reason that sector is so big is because that's where all the military hardware is hidden, right? So their input-output table hid stuff. So there were people there who were very aware of what was going on, and I felt incredibly naive, right? It was like, we go to present the stuff in St. Petersburg, and I remember reading in the Herald Tribune that morning that Putin had basically essentially fired all of the oblast governors, like 91 of these guys. So you can imagine a US president coming in and says, I've decided I don't like the governors that you guys have elected. Here's a new set for you. I'm going to appoint the governors. That's essentially what happened, just like a stroke of a pen. And it's amazing how naive we were at the time. We still had this idea that once they get wealthy, this is going to change. And it's anyway, so it's amazing. So now when I got that model running, I went and presented, I did a summer school course with, what's his name, and at the Ruhr Summer School course with Clausen, yes. So Clausen's course was fun, and he had a student there, Sebastian Rausch, was a graduate student. And he was a very good student, extremely smart guy, really nice guy from a very intellectual family. And during the course of the thing, I did a section on dynamics, and we talked about Ramsey models, and we talked about the OLG framework. And suddenly it struck me I can still remember over lunch with Sebastian, I was talking about this, said, shit, we could use the technique we used in Russia, we could use that for OLG. So he and I then set out to work on this, and he ended up going into his thesis. So this was a technique that we developed together. very cool. So basically, because if you think about, you either have lots of households from Comstat, or you have lots of households that are born at different points in time, or there could be households that are poor households and rich households. In the Auerbach-Kotlikoff framework, you can have poor households and rich households. What's the difference between poor households and rich households in the Auerbach-Kotlikoff setting? Oh. Poor households have high discount factor. Rich households have a low discount factor, right? So you can differ by their patience, right? That's one way of representing things. Or they could just have a bad draw. So there's differences in terms of explaining how things happen. So basically, what's nice about this is there are many ways in which you can imagine households being differentiated, and the sky's the limit. You could have households with one parent, you could have households that, there's all sorts of different ways that you could get at this. And so this is a classic example where being able to expand the dimension of the model, but not have it influence the runtime other than by a factor. Notice the factor I have is maybe a factor of 10 or 20. And it's all just iterative adjustments. So the point of this is that once we have our representative agent model solving, then the idea that you can add lots of heterogeneity and it doesn't really increase, this is really great because the evaluation of the demand response to households is really easy. So we proposed this decomposition method where a large scale OLG economy could be solved through computational equilibria for a sequence of related Ramsey optimal growth problems. So to illustrate, you could consider the canonical Auerbach-Kotlikoff OLG model, closed economy, rational forward-looking households with perfect foresight, the households choose time paths for consumption and leisure over their life cycle. One of the cool things in this model is you can put in leisure and you have an upper bound on how much time they have available for leisure. So you can have endogenous retirement is one of the features that happens in this model. People who get older, they have a shorter horizon to, they choose not. So that's one of the things that's cool in this thing, that and you can also modify the model. We had a student, I had worked with a Danish student. What was his name? So the Danish student had this cool model where he had endogenous education decisions. So you can choose to allocate your time to getting educated. So there's lots of ways in which this model could be made more elaborate. You can have a large number of heterogeneous households within each generation that differ with respect to labor productivity, other behavioral parameters. Firms with constraints to scale activities operate on perfectly competitive markets in this first example. And the government agent collects tax revenue to finance public provision, right? So this has got the fundamental elements you have are the same as in the Auerbach-Kotlikoff model, but suddenly you have this dimensionality constraint is lifted, so you don't have lots of households. So here now is the representative household model. So Z of GHT is the decision of how much what composite consumption is. That's C is goods consumption and L, which is leisure, by generation G of household type H in time period T. And they operate in different, so T is when generation G, their first economic choices are made in year G. So you're modeling, if you had households that were modeled, it's kind of like 20 years old is your first year, you make a decision, or 18 or whatever, and then you make a decision up to whatever, 65, or as I get older, the horizon keeps getting longer, right? So make decisions to make it up to 80, I think. So that's the decision they're making, is about the Z, and then the Z then is a composite of goods consumption C and leisure. And then we have this decision about, this is going to be omega is their endowment. And this is going to be the next iteration is keeping track of their asset position. Consumption plus investment is less than or equal to earnings on wage earnings plus their capital stock. So this is keeping track of their asset position. They have a capital, there's a certain amount of capital they own. There's an upper bound on how much leisure they are able to take. And so this is just a general. Now, most of the time we'll assume we have complete markets. So therefore, you don't need to track assets for every household, but you could if you wanted to. So there's different ways you could put. The beauty of this is if you want to put constraints on the choices through liquidity constraints or other types of decisions for generations, you can do that because the generation calculation is done independent of the macro model. So essentially think about it as we're changing what the consumption response is, and that's going to go forward. So this, then we have asset position, and then firms maximize, minimize cost, taking prices is given, and they earn zero profit. So that's going on. So we have these OLG constraints. So within the model, you have to keep track if you're working on a taxation over the infinite horizon, or you might want to say that therefore you have to pick the clock straight, or you might want to assume that that this has to be balanced on a period by period basis. The example here, we have each period T public expenditure has to be financed through tax liabilities. And then we have labor supply, then is the aggregate labor supply from each of the households. Aggregate investment is the investment or savings decisions of all the households. Capital stocks depends on, the capital stock is fully owned by the households and generation. Of course, in a model with perfect capital markets, all goods are in the same rate of return. So we don't easily identify exactly which assets are owned by which households, but this gets, you get at the idea here. And aggregate consumption is consumption of all the households. And then you get these 9 and 10 give you this aggregate capital stock and aggregate output. So this is one that doesn't have multiple sectors, although the code that goes along with the lecture has multiple sector examples. So this is then just this projection method. It's a simple thing. We solve the Ramsey model. You take the prices back from the Ramsey model, you evaluate household demand functions, that's life cycle decisions by the households. And then you recalibrate preferences, so you retarget the representative agent. So all you're doing is just tweaking the representative agent choices to represent what the households go, and then you go forward. So this is one that basically, it's like it projects on, for example, if you wanted to have the households be subject to liquidity constraints or other things, that's fine. And essentially what you're doing is you're calibrating a Ramsey agent whose preferences mimic what the capital constraints are on the household. So there's lots of flexibility here about how this works. This gives us a partial equilibrium relaxation OLG, which evaluates household demand functions. So when we evaluate household demand functions, the macro prices are fixed. And that's an iterative procedure. And the whole point is step one is costly the first time around, but the beauty of this would use path or other types of, if you can solve the Ramsey model with optimization or equilibrium, but the point is, as long as it's not an interior point code, you can solve each successive round solves faster because you're starting right at the solution. So therefore, the time cost is mainly the first iteration, and thereafter it goes really quick. So here's the Ramsey model, and here we have this theta k sub t is iteration k, what the weights are, and z bar kt tells us what composite consumption is in that period. So we're going to calibrate to exactly what the leisure demand and the consumption demand and what the aggregate. So all that stuff gets calibrated in each iteration, and they have a K on them indicating where that goes. But otherwise, then you have it's basically a Ramsey model, and every iteration we just change what the characteristics are of the Ramsey model. I also show here early on, I showed that state variable targeting, and that's what's going on here. You have this is the initial capital stock, and then you have the let's see, no, that's the initial capital stock. Oh, those guys are fixed. So where's the, oh, there's KT plus 1. So K hat T plus 1 is the post-terminal capital stock. And so that's using this RJDC paper in 2002 for doing that. So we get initialized stuff. That's the first iteration. We tie the thing down based on what we are. And again, this is what my new work with this is trying to work on developing a technique so that we don't have to be along a steady state. In this earlier work, we always had a steady state equilibrium. So tell us what the interest rate was fixed, the same over time, consumption growth rate was fixed, everything, the economy was simply just expanding. Whereas here, in more sort of empirical applications, you like to have this be non-stationary. So here's a diagram that illustrates how the timing works. So the Ramsey model works on, is a numerical model that works on period 0 through big T. And then, whereas the OLG model, we have agents who live off the end of the model. So they're agents who are born prior to big T, but they die, they leave the economy at a later date. So therefore we have to basically project what happens to prices out in the future. So that projected prices, we basically have R infinity. We know we can observe observation of assumptions about growth and discounting, tell us what the interest rate has to be at infinity. And we basically make this assumption that our model goes far enough that we're close to the steady state by the end of the horizon. So we're relying very much here on this turnpike properties, these models. So because you're optimizing over the model, the policy will always be close to a turnpike toward the end. That means the model will tend to go toward the fastest, the optimal path at the end. But the reason it's called the turnpike is it's the same as if you were in Madison and you say, I'm going to go on vacation to California. I know where you're going to drive, right? I know how you're going to go because I know that if you're going to take the shortest path to go to California, you're going to get on Interstate 80. And I know the fastest path is going to go down 151. Yeah. So therefore, the turnpike property says you always go on the fastest path. So therefore, where we go at the end of the model doesn't matter. What matters is the transition path, and that will be the property. So therefore, we want T to be far enough that we're close to the steady state, but it doesn't have to be ultra long. And for that's our basic point about dealing with these Ramsey models is if you want to do a Ramsey model where you have 10 goods, 10 sectors, forward looking, you have to basically, you can't tie down lots. You can't do a 300-year horizon. You end up having too many dimensions. So that's where we rely on this property. So there's the recalibration. We calibrate, we solve the model, we take the prices back, we reevaluate the household responses. That tells us what the consumption choices, leisure choices are. We then adjust, we update what the discounting should be that's consistent with that. We re-specify what the shares are. And the crucial thing is that all we lean on here is the algebra that I went through that in the documents I gave you yesterday about the calibration of CES preferences. That's all. We're relying here on the fact that we get observations and recalibrate. And so we want to basically see that we can get this guy to go. And this shows you an example. This is a testimonial proof of convergence. So here we have 34 iterations. So that the first one shows you what the Ramsey model would give. And then you have, notice that this is from 6 to 8. So therefore, this is the deviation. I'm not sure exactly. This is the overall impact in the Ramsey model says around the impact of this policy shock of about 7 would be a reduction from 8% to 7.6%. And then the OLG model is a little bit different. So there's an aggregate difference. We don't find, oftentimes there's not a lot of difference understanding, and I'm curious, I'm looking forward to doing how this works with the IAM model because it's kind of cool. One thing to bear in mind is it looks like you have to solve the model a lot of times, but bear in mind that every time we solve the model, we have a closer and closer approximation. So it's basically just do 2 steps and you solve. So therefore, the fact that there's several iterations, you may spend most of your time maybe spent on iteration 1. And if you're doing a model that has an investment dispatch electricity model, the time you spend on the macro stuff is basically negligible compared to the time you spend on the electricity model. So this thing is all relative. So overall, the cost of going to OLG is not very much. So that shows the approximation error. So we know that. So again, my life has been made up of using algorithms which work well, but can't be proven to converge. When I first got into this game, I spent most of my time feeling incredibly inadequate because I had no proof of convergence for our Newton method. It was just like, it worked, but there was always this apologies, but I'm sorry, I can solve this model 1,000 times faster than you can, but I can't prove it's going to converge. So therefore, your algorithm is better than mine. That was sort of the state of affairs in 1980, right? So, but the fact is that this is an adjustment process, which I find very intuitive, and we can construct examples where it doesn't work, right? And so you don't have to look very far. One of my favorite ones is, let's see, I have it. There's Scarf's globally unstable. This is a model where it's a 3-agent, 3-commodity exchange model where agents, you adjust the endowments. So one guy likes what the other guy owns and so forth. You put it in a circle and you make the elasticities low enough. The Tatnamon process won't converge. So you just basically, where there's an excess demand, you raise the price, excess supply, you lower the price, it'll just go into a circle. It never converges. So that was a paper from Herb Scarf in 1962. If you take this model with this algorithm, This shows the direction of, it's not exactly the same direction adjustment path as the Tatnall path, but it doesn't converge. It'll wander around and not go there. So we know this doesn't work. We can construct examples where it's non-convergent, where it basically doesn't work, where there are high income effects. So we know that this is the case, but for OLG, we've always found that we don't have any trouble with these things. Now, understanding what it is, of course, it's not going to be operational here. So the algorithm is surely inadequate for approximating equilibrium that are dynamically inefficient. So you have models where the growth rate exceeds the interest rate. It's not going to work. So there are cases where you have things the planner's problem doesn't work and this method won't work. But if the planner's problem works and you can solve a Ramsey model, then doing the household model is not putting in different households. It's work. Clearly, if you want to calibrate the model to a non-stationary baseline, people have strong assumptions about what happens along the baseline, and getting this thing crafted to match exactly a given baseline path could be tricky, and it is tricky, but the actual calculation, once you get the thing operational, it's not a problem at all. And I think that the policy insights you get, again, I think the key thing these days in CG is distributional consequences of policy. What happens to which agents is really important. And this is the dimension that I think is potentially very useful. So material you have here is you have a template SR model for the static model I went through at the beginning. I have a little exchange model that works. We have this paper that has the decomposition method for OLG models described. We have both the MCP and the MPSG code for the OLG model, which solves both by integrated, so we can solve the MCP where we put it all together. We're doing it iteratively. And we also have code for a small open economy Ramsey model for calibrated to Canadian multisectoral data. And there's like 4 different aggregations of the data set. So you can see an example of this that operates. Yeah, so that's what I have that goes along. And you get a sense about computing times depending on the size. So I guess at that stage, I would ask, I'm not sure, Jim, I told Jim I'd talk about this stuff. He may have been hoping for me to talk about the OLG stuff. I apologize, I didn't have that stuff done. Maybe yeah. So I got this stuff all here. So I'm open to requests from the audience about the stuff. I'm done a little bit early. I don't think I'm going to spend the time going through the code, but I will share the code with everyone. So yeah, I think that it's better just to share it because it's kind of specialized. I don't have people's eyes glaze over. So
Hey, Tom, thanks for going over that. Do you have time for a couple questions? You're muted.
I turned off my microphone or my speaker. Now your speaker's on, you can talk and I can listen.
Great. Yeah, so this is great. I mean, like that's the, I can see like a lot of applications for that method, applying it to like either like, I guess there's US rep, not an OLG application, but then yeah, it would be great at some point if we could get, a like WiNDC hooked into that with like an OLG model to start playing around with and, doing some distributional work. Cause like, as we had spoken about, a couple of weeks ago, like this, a lot of the household data sets that we're trying to develop and work with, if we could have like a very rich household data set, it would be great to be able to hook that up. And I guess like Jared Carbone and John Becker are also working on this as well. And I guess I was doing some email exchanges with them. It might make sense to have like a little OLG meeting of, different folks that are kind of like working on this and see if there's, opportunities to collaborate or kind of learn from each other. And the non-stationary growth path, I think that would be of interest to us. And, Kirk Phillips is on here, probably also interested for CBO for this work. So I think that'd be really, really quite terrific.
Very much so.
So Kirk is from CBO.
Last time I checked, yeah, they haven't fired me yet.
That's great. No, I'd hoped to actually have a template model running, Jim, and I didn't get around to getting it finished. So but happy to share what I have. And I'm very keen to do this because I think it looks to me like it's relatively low hanging fruit, particularly if we go the same strategy of having the first thing to do is do the simplest case. We just have one household per generation, steady state growth path, on a balanced steady state growth path. Just get something running and demonstrate that the overhead is modest for up to 20 sectors or so, then, and for all 50 states, then you're home free, right? So I think that's the most important thing, is to demonstrate that you're able to do it. Because it's always this thing of like, you want to try to do things sequentially. So anyway, yeah, I'm
Well, so that was the question I had. Like, would you, because when I was talking with Jared and John, in their, they were looking at doing, like, they I guess they have an OLG model, and then I asked about regionality, and they said, well, they thought the dimensionality would increase too much, and they didn't think it would be able to solve. So I guess I was kind of curious about, like, have you worked with OLG models with both sectoral and regional dimensions?
So the thing is, remember here that if you're trying to solve an integrated model, then that comment is definitely true in spades, right? You have this problem that you inherit. As soon as you put in an OLG household, then you inherit lots of households, because you have every household.
Yeah. And in fact, if you can get the OLG model solving, the dimensionality of adding the additional sectors is actually pretty small compared to the dimensionality just from all those generations and types within generations.
Right. So so my point, I would point to the WiNDC data set is designed for doing dynamic modeling. It's like we produced this recalibration that accounts for that. And I did the example, we had the Ramsey model I presented last year. I didn't present one this year, but the thing is, that's something we intend to always have a generic Ramsey model. And as soon as you have a Ramsey model, it does have some overhead, because you have to have representative households in every state. So you have 50 states. We found that we were able to solve that pretty easily. And then if you use this sequential recalibration technique, you don't have any additional changes. It's just, you can swallow whatever you're able to solve in the Ramsey framework. That's all you need to track of.
No, that makes sense. Yeah, I mean, I get, the interesting applications. Well, I mean, CBO has their long-term budget outlook, and so I think, like, taxation deficits, like, all of that is very interesting. On our side, introducing like climate damages and impacts and things like that could be really interesting at sort of like the regional level, and also with household heterogeneity.
Yeah, I mean, we have this is the stuff with the integrated assessment. I'm definitely doing that this summer. I'm working with Christoph. We're collaborating with the folks from Environment Canada. So the thing is that this is definitely something we'll be doing, but I'm very keen to get this involved. So if there's ways that we could get together a working group on this would be a nice thing to do. Maybe not permanently, but for a month or two this summer, that'd be fun to work.
Yeah, that'd be great.
We put on a seminar at CBO, gosh, 2 years ago, pre-pandemic, 3 years ago. And we had Larry Kotlikoff bring his model in. Ken Smetters with the Penn Wharton budget model came in. The Joint Committee on Taxation has a model. All of these are models that are designed to, go to the data to be used for forecasting and projections. And I don't think anybody had a method that would solve in the time it looks like this one would solve. Everybody is using those models, is still doing the old time path iteration that Auerbach and Kotlikoff originally did. That's what we're doing with ours. And it takes, hours and hours.
Now, I'm impressed by their method, that it actually works. It's amazing in 85 that they could come up with this.
Oh, yeah.
It's great. But the thing is, this technique, because particularly if you're using modern computational tools for optimization or equilibrium calculations, you're getting these subsequent iterations are really quick. You load it and boom, it gets updated. So
yeah, no, this is, I was commenting with Jim on a side chat that this is really ingenious, and once you get it explained to you, it's go, oh well, duh, this is so intuitive, but ex post everything's hindsight's 20/20 or whatever.
the thing that's weird about this is I got pulled off onto working on other things. And I put this aside and I hadn't worked with it. And then I started a couple months ago looking at it again. I was thinking, man, I can't believe I didn't do more with this algorithm. It's like, it's really great that it works so well. So
No, I'm really excited about this. This, I think, has a lot of potential. And again, like I said, I don't think that the people that are using this for using OLG models for policy analysis are all that aware of it. And they ought to be.
So Tom, what IM model are you using? Is that the one you developed for?
We have a new version. We have a version of DICE that's putty clay. So we have a putty clay model with uncertainty. So it has, we basically didn't bring the technology piece, but yeah, so we have a nice, that's where we're currently working with. We also have a much more, the Canadians want to have a multi-sectoral one that has energy transitions and so forth. But for the purpose of the OLG work, it's basically something that's like DICE, but has elements from Merge that I think are potentially important. We're mainly emphasizing the key insights we're getting from this is that the putty clay matters a lot for net zero simulations, the transition path, and so I'm excited about this work as well. I think it's cool, but I think that for OLG, part of it, my interest in this also comes about. I'm terrible. I'm getting old, so I can't remember the names. But there's a guy here at Wisconsin in medical ethics. He's a philosopher in medical ethics, and he's working on ethics of climate policy. And so he and I are going to be running a course. We're teaching a course on ethics and markets and climate policy next spring. And so I also have to get this running because I want to be able to have a dialogue with him about ethical outcomes in climate.
Oh, that's really interesting. I mean, I can see like energy transitions and climate impacts could be very, very influential in that. So yeah, very cool.
So cool. That's what I got. We're gonna we'll put all the stuff together for folks going out, and that's we have going. I don't know. Normally we're scheduled to go till 12 right now, or what? But I don't know if there are any other questions. I'm happy to handle them. Otherwise, we might declare victory early and then come back half an hour earlier. Would that be 12:30? Yeah. So then that way, I think what we'll do is come back at 12:30, and then at 12:30 for just half an hour or so, I'll just go through. I have some code for reading this reading this XEO base data set, and I'd love to get your input, Jim, or your group. That if anybody's worked on this, I'd love to have people have a little bit of a dialogue about how this works.
Oh yeah, so I looked at that data set years ago, but not recently. Yeah, but happy to have that conversation. Yeah. And I guess I had put a few notes in the chat about things I'd like to comment on maybe in the afternoon. So one was like, yeah, I guess showing people the spanning operator and the nesting operator in MPSG, because I didn't know about that until, well down my path, and it was like, yeah, anyway, so it's worthwhile to kind of cover that, I think, for everybody. And then like MPSG 2.0, and then I was also curious about your thoughts on the extending mathematical programming that Michael Ferris has, been working on, and GAM seems to be promoting that on their website quite a lot. So I don't know if there were applications for us or not.